All right, recording is rolling. Welcome to Wednesday, September 20. I've got Atwood Lab lined up for you guys. Now, if you guys remember yesterday, this paper, we did a friction lab yesterday. It's a two-part friction lab. You guys were looking at coefficient of friction from different points of view, right? Dragging versus lifting sort of deal, and then like tilt the table. But that same page is the opposite side. I've got a two-part Atwood Lab for you guys, right? So I'm gonna walk you guys through what I'm looking for, what the challenge is today, give you guys a few tips, and then send you back to the lab area. Right? And then the last few minutes of class today, I'll go over those solutions with you guys. But yeah, see if you guys can figure this out. This challenge question, right? All right. So let's start with the classic double elevator Atwood. You guys have got some of these pulleys. Ooh, oh, look at that low friction pulley. Look how well that spins. Oh yeah, you guys got some string back there. You guys got boxes of lab weights, and the question is going to be, like, what's the acceleration? Or here, did you guys think if these were different masses, like different weights, you think it would accelerate? Like, accelerate, right? The challenge is, can you figure out what is that acceleration as a function of each of the masses, right? So the way I might phrase that is like, what's the acceleration of the system? What a lot of textbooks do, or if you look like an AP question, is they might say like, what is the downward acceleration of the large mass or the upward acceleration of the small mass, something like that. Right, might be how it's phrased. Let's do some examples. Let's start with some boundary conditions, things that you might be able to logically figure out. Like, what if this was 1 kilogram versus 1 kilogram? What would the system do? Exactly, equilibrium, right? I mean, you're holding the pulley in place, of course, right? So equilibrium, right? Which means zero net force, zero acceleration. It's just going to stay there, right? So you let them go, it just doesn't move. That would be zero acceleration. Okay, so that's like one boundary condition. The other boundary condition, the other extreme is, what if you put all the weight on one side? What if this guy's 1 kilogram and this is just an empty string over here, and you let it go? Is it going to accelerate? Definitely. How much? How much is it going to accelerate down? Boom, the full rate of gravity, about 10 meters per second squared, right? So something like that, the full rate of gravity. Okay, now here's the tricky thing. What if this was 3 kilograms versus 7 kilograms? Is that still going to accelerate? Yeah, probably somewhere between these two boundary conditions, right? Somewhere between 0 and pure free fall, right? I'll talk about this one on the right later, right? Let's focus on this one here, the classic double elevator Atwood. Right? So right at the very bottom, the question is, what does the acceleration say as a function of the masses, the input masses? So you could have any general M1 and M2. Might be 3 kilograms and 7 kilograms, might be 4 and 6, might be 1 and 9, right? So you can put in any input masses, and you can predict, ooh, I think it's going to accelerate this much. So here's how we're going to do it. You guys are, of course, going to do this empirically, hence lab. Right? So got this table. Let's go left to right. I gave everybody the gravity field. 980. Guys, why do you do 980? Look at the units really closely. What units is that? Centimeters per second squared. It is okay today if we just do centimeters instead of meters, if we do grams instead of kilograms, right? Okay, so we got centimeters and grams today. Okay. So centimeters per second squared. So there's pure free fall, 980 centimeters per second squared. Right? Record each of the masses, M1, M2. Right? Guys get that? Right. Now, do you guys think here? This is a really abstract idea. You guys think you want to make a pretty long string? You guys want the string to probably be at least a meter long, right? You guys think probably be pretty good, right? Right. Just an idea. What do you guys have back there? Give you guys some help when I'm back there too, right? So record the masses. Now these next two columns help you guys out a bit. Help you guys frame this lab, direct you guys a certain way. Take the difference of masses, like the absolute value difference, and then the sum of the masses. That'll be important later. Right? Now these last four columns have to do with kinematic motion, like getting the acceleration. At this point in the class, you guys have two different perspectives on acceleration. The kinematic perspective had something to do with the rate change of velocity, and the new perspective, like the dynamic perspective, has to do with Newton's second law. It's like forces acting on masses. Let me flash those two posters up here. Right. Did I tell you guys yesterday, acceleration is kind of like the bridge between the kinematic motion that we were doing a few weeks ago and the Newton's second law motion dynamics that we're like doing now, right? Because here's the three amigos. They could all involve acceleration somehow. And here's where acceleration comes from, like why things accelerate. Because it's like a force acting on a mass, right? So acceleration is like the bridge. And you can use kinematic motion to figure out what acceleration is, right? And then the challenge today is to figure out how do the masses enter into that. Right? So let's focus on these last four columns. So x in centimeters, like how far would one of these masses move in centimeters, right? I might do very simply like the exchange distance. Like if this moves down 100 centimeters and this moves up 100 centimeters, then 100 centimeters, right? So you can call that 100 centimeters if you have a string that's at least that long, right? Time in seconds. Ooh, you guys can have some stopwatches back there. Can you guys go, right? Time it, how much time it takes, right? Ooh, maybe do 3 trials and take an average, right? That's good practice, right? To help mitigate random error. Sometimes you're fast, sometimes slow in the stopwatch, right? My AP students, I tell them there's always an FRQ, and that's always one of the points on the lab FRQ is do multiple tries, take an average to mitigate random error, right? This last column says acceleration. You can calculate that, right? Now, how can you calculate that? Well, look what we got so far. We got how far and how much time starting from rest. Is that 3 kinematic values? That is, so in principle, you can calculate acceleration. And in fact, here's exactly how you do it. Look here, x equals 1/2 at squared. Now that's true starting from rest. Hey, that's the college equation. You guys remember college? Right? That's x equals 1/2 at squared. You can algebraically rearrange that and say the acceleration is 2 times the fall distance divided by the time squared. So you can calculate the acceleration. You guys get that? Right? You guys can get that in centimeters per second squared. I bet this number is going to be somewhere between 0 and 980, right? Depending on the input masses, right? And that's okay. So get down to this box at the bottom. Right? What is the acceleration? You guys see that 4 of these columns have been starred. There's some relationship among these 4 columns. There's some way you can multiply and divide the first 3 to get the 4th one, right? At least in textbook theory, or it should be pretty close. Let's see. So we got pure free fall. We got the difference in masses. We got the sum of the masses. There's some way you can multiply or divide this, where it should land you pretty close to the kinematic calculation of acceleration. Okay, right. You guys get that? All right, let's switch over and look at the second half. I should tell you guys too. The amount of time you'll have in class today, you might be able to do like 2 or 3 of these, and maybe 2 or 3 of these if you're working pretty good clip. But you won't have time to do like the whole table. But that's okay. I'm not looking for the whole table. Right, just as much as you can. Right. Now, what's sometimes called like a modified Atwood. If you look at like AP questions, they like to use that phrase, the modified Atwood, where there's only one weight that's hanging, and you got another one that's like sliding across the surface. I'm gonna have you guys tape weights to take these masses to Hot Wheels cars. So you guys can take some tape, right? Well, there's probably some set up there from earlier today already, right? Guys, what's the purpose of the Hot Wheels car right here? What does that do? Reduce friction, right? So friction could be negligible. So you can say there's 0 friction on this, right? Well, guys, if there's 0 friction, let's see, I bet this has a weight, but also a normal force balancing it out. Do you guys think the weight and the normal force balance out? They would. So what's this good for? If it's a larger mass, is it going to slow the system down? I think it will, because larger mass has more what starts with an I? Inertia. Exactly. That's what I'm looking for. Inertia. So larger mass would slow the system down, right? I said, throw this over here, string over, pull A over the edge, right? Let it fall. Right. You guys said, guys, do you guys think this car has some mass too? You guys think the car has some mass? Right. If you want to call the car 30 grams, you can do that. So if you have like 500 grams here and 30 grams here, you call it 530. If you want to get a more accurate value, there is a triple beam balance back there. So you might get a car that's like 34 grams or something. Okay. You guys good? All right. The table is a little bit different because it's a little bit different setup. The answer is a little bit different, but they're not crazy different from each other. They're kind of similar type format. Okay. All right, you guys good so far? All right. Let me give you one last tip. All right. So as a matter of lab practicality, what do you guys think is easier to time? A fast acceleration or a kind of a slow acceleration? What do you think is easier to time? Slow acceleration, right? Right. Now, both these have, how could you possibly get a slow acceleration? Right. If these masses are very different in value or very close in value? Close in value. I'll give you guys a tip. What if you start off with like 200 grams and 200 grams, so it doesn't accelerate all? Then you take a little tiny 20 grammer, boink, and attach it here. Could be 220 versus 200 grams, and that'll accelerate probably nice and slow enough, and you get a pretty good timing, right? How about on the modified version? What's going to slow it down? Let's look at this race car right here. Should this have a large mass or a small mass? What's going to slow it down? How about a large mass, right? If you put 1 kilogram here, I bet that slow it down a pretty good amount, right? What about the hanging weight? If you use a large or small hanging weight, what's going to slow it down? How about a small hanging weight, right? A small weight here and a large mass here. I bet that accelerate nice and slow, right? Okay, right. All right. So that's all I want to tell you at the start up here. I'm going to stop this video. walk back there, help you guys out. And then the last few minutes of class, I will show you guys the solutions.